Let's dig in. We're here to talk about service mesh to service mesh. Here's the part where I tell you I am definitely going to post the slides on my site tonight. I've been that person chasing the speaker and it didn't work out very well for me either, which is why you can go to robrich.org. Let's go right there right now. You can click on presentations here at the top, and here's service mesh to service mesh here at All Things Open. You can grab the slides. They're online right now. Feel free to jump into the slides, heckle me about the things I haven't said yet. They're available online right now. While you're here at robrich.org, let's click on About Me and learn about some of the things that I've done recently. I'm a Cyral developer advocate. If you're struggling with your data mesh, I would love to learn from you. I'm a Microsoft MVP, a Docker captain, and a friend of Redgate. AZ Give Camp is really fun. AZ Give Camp brings volunteer developers together with charities to build free software. We start building software Friday after work. Sunday afternoon, we deliver the software to the charities. Sleep is optional, caffeine provided. If you're in Phoenix, come join us for the next AZ Give Camp, or if you'd like a Give Camp here in Raleigh, or wherever you're connecting from, then hit me up on email or Twitter, and let's get a Give Camp in your neighborhood too. Some of the other things that I've done, I do a lot with Docker and with databases, SQL source control basics, minus chapter 8, that was a lot of fun. And one of the things I'm particularly proud of, I replied to a .NET Rocks podcast episode. They read my comments on the air, they sent me a mug. Woo! So there's my claim to fame. And if you'd like a .NET Rocks mug, no, I'm just kidding. They actually don't hand out .NET Rocks mugs anymore. So yeah, I have one of the coveted ones. So let's talk about service mesh. We talked about this guy. Do you remember when you learned to drive? Do you remember the freedom that it was to be able to get beyond where your bike could go or where your skateboard went or how far you could walk? Do you remember how cool it was to go way far away? Imagine this empty road where you can drive as fast as you want to and get it to wherever you need to really quickly. Well, in time, maybe this road gets a little congested. Our country town is now kind of, well, full. So how do we solve this? Well, we can set a traffic cop at the edge of town, and anybody who's coming in too fast, he's going to slow them down. We're now all traveling at the same speed. Now it solved our congestion problem. That was great. But now we're not really getting there as fast as we wanted to. We're not really getting there as efficiently as we could. We optimized for uniformity, not for expediency. Probably what we want is something like this, where our cars can communicate with each other, where we can prioritize traffic, where emergency vehicles and those people who really want to drive fast definitely can, and those people who want to take more of a leisurely pace can do that as well. In this scenario, our cars can communicate with each other and ensure that there aren't traffic jams, that we can prioritize that traffic correctly. We're going to see similar analogies as we start talking about service mesh, where we look at mechanisms where maybe traffic jams happen, mechanisms where we can start to prevent that. And does the traffic cop really solve that? We're going to dig into what is a service mesh. We'll see some of the features that a service mesh can provide. We'll take a look at pros and cons of a service mesh, and we'll get to see a demo of both Linkerd and Istio, which will be really fun. I look forward to your questions because I'm sure we're going to hit that spot in my knowledge where we fall off the cliff, and I'm really excited to be able to learn from you too. So what is a service mesh? A service mesh manages network traffic between services in a graceful and scalable way. Or said differently, a service mesh is how you can observe, control, and secure the traffic in your cluster. Observe, secure, and control. We'll keep coming back to that because observe, control, and secure are things that we need to do inside of a Kubernetes cluster that may be difficult with just standard microservices. So observe. Our goal with the service mesh is to be able to watch the traffic flowing into and out of different microservices and to be able to understand if that's normal or if that's suspicious or unexpected. As we start to understand what is normal, we can start to create policies that might control that in a certain way. We can say, no, I'm really not going to allow traffic into this service. And then finally, secure. Our goal is to create mutual TLS between each of our microservices. And though we definitely could embed that in each application together with the configuration, together with the certificates, together with the trust chain, if we can put that in more of an external spot specific to our service mesh, then we can get that same level of security, mutual TLS between our services, but without that barrier that our playing with cameraman is fun. We can get that level of security without the barrier of implementing that in each of our microservices. We can do that once inside of our service mesh and still get that security. Observe, control, and secure. So what came before us? Well, before we had a service mesh, we had a monolith. Now, a monolith was great in that we could deploy all of the pieces together. We saved up our changes. We got to a point where we're done, and now we spend the weekend deploying it. You remember those calls that start, say, I don't know, Friday at 4 and ends somewhere around Sunday at 2:30? Usually by like Saturday mid-morning, things are starting to work again. By Sunday, everyone is just trashed and still trying to deploy. Monoliths were great in that it avoided that pain of deployment. As we got to containers and deployment was no longer a concern, we could deploy a whole lot faster. We could deploy a whole lot smaller pieces. We could deploy in mechanisms that just made it a whole lot easier to use. Microservices solve the deployment concern. That's cool, but with a monolith, my internal functions were internal. With microservices, my internal functions have IP addresses. So how do I know the things calling my internal functions are doing so correctly? Is that really the way I wanted my internal functions called? As we moved from monolithic to microservices, we had this communication problem between our services. As we start talking about microservices, we'll talk about traffic in two different ways. We can talk about north-south traffic, traffic flowing into and out of our cluster. And we can talk about east-west traffic, traffic flowing between our microservices. The cool part is the service mesh is able to handle both north-south traffic into and out of our cluster, as well as east-west traffic, traffic flowing between our services. So what came before us? Well, we had the microservices, and we wanted to upgrade to an API gateway. Now, the cool part about an API gateway is it's this fence around our cluster. Nothing's getting in unless it passes by the traffic cop. And the traffic cop is very specifically going to make sure that we're all uniform traffic. Well, that's great. The traffic flowing into and out of our cluster is now under the control of this API gateway. But what about the traffic flowing between our services? Now, one of the tenets of microservices is that they should own their own data store. How are we doing? These microservices are calling each other's data stores. They're calling each other too, but the API gateway has no visibility into this. The API gateway's job is to defend the boundary of our cluster, the north-south traffic. The API gateway can't see into our cluster to see this east-west traffic. And so, though our API gateway, though our traffic cop was really good at ensuring uniformity coming into town, our API gateway knows nothing of the mayhem that we've caused for ourselves inside the town. So how does the service mesh work? Without a service mesh, if service A wants to talk to service B, service A opens a connection, connects to service B, and we're done. With a service mesh, it's a little bit more. So service A would like to talk to service B. Service A gets deployed with this sidecar proxy. In this case, it's an Envoy sidecar proxy. Now, both of these are deployed inside the same pod, and so they have a network boundary around them. Nothing is getting into the service that doesn't flow through the sidecar proxy. When service A is ready to connect to an external service, service A connects to its sidecar proxy. Now, the sidecar proxy checks in with the control plane. Hey, am I allowed to connect to service B? In this case, the control plane is going to say yes. And we create this connection off to service B's sidecar proxy. Now, service B was also deployed with the sidecar proxy. And so service B's sidecar proxy will go check in with the control plane am I allowed to accept traffic from service A? In this case, the control plane says yes, and service B's sidecar proxy forwards the traffic off to service B. Service B replies, and that connection goes back to service A, and we've established that connection. Now, what's beautiful here is that between service A's sidecar proxy and service B's sidecar proxy, we can create this mutual TLS connection that has a trust chain back to our control plane and maybe back to our PKI infrastructure in our enterprise. This mutual TLS connection means that any other sidecars, any other containers running in our cluster are not allowed to see this traffic. We have created security in depth between our services without having to implement it in service A nor in service B. This pod boundary creates a local host connection between these two pieces, and anything flowing outside that is flowing through mutual TLS with a trust chain back to the control plane. Now, let's swap out service A with an ingress controller. Now, if we have north-south traffic flowing into our cluster, it's going to flow through this sidecar proxy. It will check in with the control plane and will finally forward it off to the service that needs it. Or we'll swap out service B with an egress controller. And now our services can connect with outside things in a similar way through this mutual TLS secured mechanism through our cluster. Both north-south traffic and east-west traffic can be solved with the same metaphor. So the cool part is now, because we have this proxy connecting all of our services, we can observe, secure, and control the traffic flowing between our cluster. We can observe it. Our traffic is flowing through this sidecar proxy, and so we can watch for messages coming in, HTTP status codes coming out. Is the response time taking a really long time? We can observe that mechanism. We can also now control it. We can create policies inside of our service mesh that says, no, I'm not going to let you connect service A to service B. We'll need to work with our developers to make sure that our application is built not to expect that, but we can create those policies so that our services can connect to only those places that they need to. And finally, because we have mutual TLS secured through that trust chain through the control plane, we get a really elegant security story without the need of implementing that in each of our services. Now, what's really great here with this service mesh is we have that mechanism where we've been able to connect these things in elegant ways. But this is not just the end goal of what we've got. Because we're proxying it, we have lots of other things that we can do here. We talked about logging so that we can watch the traffic flowing between our various services. We can keep track of the status codes and the response times. We can understand over time, is that service healthy? Is it unhealthy? Hey, if it's unhealthy, let's evict that pod and create a new one. What's really elegant, because we're proxying all of the traffic throughout our network, we can be able to see connections between all the services. And with that, we can build out a network topology diagram. Now, this isn't what the architect or the developers thought was going to happen. This is what is actually happening in the cluster. We can see the connections connecting our microservices, and we can build out that diagram. Both east-west traffic inside of our cluster and north-south traffic as traffic flows into and out of our cluster. Well, let's level up again. Because we're proxying traffic through all of the services, we can create really intelligent routing across our services. So for example, an A/B test that might be able to look at the content in our cluster and maybe make some choices. Let's forward maybe to service A. Let's also maybe forward to service B. And maybe they accomplish pretty similar tasks. And now let's evaluate that. Which one best serves our customers' needs? Which one best is able to do conversions? And then let's lean into that. We can create those intelligent routing rules because we're routing all of the traffic through our cluster. We could also create a beta channel. So let's create a canary release or a beta channel where advanced users can connect to new functionality and we can get additional feedback before we release it to everyone else. We can route traffic into those particular services that have that need, that have that ability. And we can also create a circuit breaker. Now, what's really elegant is as we do these kinds of network interactions in our cluster, if ever we have a network failure, well, we can assume it's a transient failure and the client will retry that connection. Now that's perfect. They'll retry the connection. Well, what if it isn't a transient network failure. What if that target service went down? Of course, all of the clients are going to retry their connections. And so the moment that service stands back up, it's going to get flooded with all of these retry connections and, of course, take itself down again. Watching that behavior happen, we can set the circuit breaker. Once the circuit breaker trips, then all of those connections can get a hard no. They are not going to get the answer. And even as they retry, the service mesh can give them a failure status. At that point, the service has time to come up, get to the point where it's healthy. And unlike the circuit breaker in your house where you have to go flip it back on, once the service mesh understands that the service is healthy, it can start trickling traffic back in until it opens it back up. Now, this is really elegant. That circuit breaker was able to self-heal our cluster without impacting any of the services, and the retry logic is built into the service mesh instead of into all of the clients. That's really great. Let's level up again. We get some really elegant dashboards with our service mesh that allows us to be able to look into all of the pieces of our system. So one of the questions that I get next, so the really cool thing, because we have this proxy mechanism, we can now step into a service collection like this and say, you know, I really think you shouldn't call each other's data sources. I'm going to block that network connection. Now, this is possible with service mesh because we are proxying all of the traffic through the cluster. We'll definitely need to work with our developers to make sure that they don't expect this traffic to happen, and therefore our application starts to fail because we blocked it. But we can start to prevent these unauthorized data connections. So the question I often get then is, well, which service mesh should I use? How about Istio or Linkerd? How about Console or Open Service Mesh? And there are many others. Which one should I use? Well, if we start comparing them based on features, we'll get to the point where most of the service meshes look pretty much the same. As we get closer to the content, then they are indeed very different. But from a 10,000-foot view, they're all moving pretty quickly. And so we can pretty much say that from a feature standpoint, that's probably not the deciding factor. Instead, let's look at the methodology involved in each of these. We will take a look at the pros and cons of each approach and really what they focus on. So let's first take a look at Linkerd. Now, the cool part about Linkerd is that Linkerd tries to own the entire stack. They're a great contributor to the Rust network stack, and they really focus on making a really elegant startup experience. What's wonderful about that is that a lot of it comes in the box and you can get up quickly. The downside is if ever you have a need that extends beyond what Linkerd gives you, then you'll need to reach out to third-party plugins. By comparison, Istio tries to collect the best of open source. So we have lots of different details that we can turn on and off based on a profile. Now, a profile allows us very large pieces of switches, but we can also get much more granular about the features that we want to turn on and off. It's collecting the best of open source, and so we'll see lots of products baked into Istio. So if you want to have a really smooth startup experience, then Linkerd might be a great choice. But at the point where you might hit a wall there, Istio might give you more features. So let's take a look at both Linkerd and Istio. Now I have different clusters with each one so that we can play with each one. Let's first start with Linkerd. So as we get started with Linkerd, we'll come to the Linkerd docs and we will validate our cluster. We can download the Linkerd binary, and then we do a Linkerd check -- pre, which says, go evaluate the cluster and validate that it can do all of the pieces that it needs to. Once we've got that successful, we can Linkerd install, and that's the point where I am right now. So let's say Linkerd check, and Linkerd check will then go through my cluster, validating that all of the components that I have installed are ready to go. Looks like everything's working out well. So now we can proceed to the next step where we do a Linkerd viz install. Okay, Linkerd viz install, we'll pipe it to kubectl, apply -f, and apply all of the details. Now I cheated a little bit. I did this part ahead of time as well, but linkerd check. The cool part then about linkerd check after you do the install is not only will it validate all the components are running, but it will wait for the components to install if they aren't already. So you notice that it spun a little bit waiting for the linkerd visualization pieces to install. Perfect. So now we've got linkerd installed, and now we've checked it again, validated everything is good. If we wanted to install Buoyant, we definitely could. And next, let's take a look at the linkerd dashboard. Okay, linkerd viz dashboard, and I'm not going to start it in the background. I'll just start it in the foreground here. And up pops the linkerd dashboard. Now, linkerd's focus is all of the things in the box, so we'll get to see all of the pieces. Let's pick a namespace. We'll pick the linkerd namespace. We can take a look at a particular deployment and see some of the particulars about that deployment. Let's also look at the Grafana dashboard. This is the one part where linkerd kind of steps outside the box. They pulled in Grafana, and the cluster hasn't been running that long, but you can see the interesting metrics that we get in the box when we install linkerd. That install experience was just really smooth getting going. Now, the linkerd dashboard is great, but we have to click through it. So let's close this dashboard, and we can do a similar thing from the command line. So we can say linkerd stats. Let me go grab that command line. Linkerd viz stat. And I will do in the linkerd namespace, and I want to take a look at deployments. Now I could definitely hook up a Prometheus sync to grab these details instead, but here from the command line, I was able to see the deployments associated with the linkerd namespace. So here's the latency associated with each one, the active TCP connections. It looks like so far my linkerd install is working, and so that is great. Linkerd focuses on that really elegant startup experience and focuses on having most everything in the box. Let's shut down Minikube stop -p linkerd demo. Let's shut down linkerd and instead switch over to Istio. Now, Istio has a similar type of getting started experience where we first download the Istio command line utility. We set it in our path. We pick a configuration profile. In this case, they're suggesting the demo profile, which has everything enabled. That's pretty cool. And then we can choose to annotate our namespaces. Now, linkerd has a similar mechanism where we annotate our namespaces. Once we've annotated a namespace, then that designates this as things that should automatically get the Sidecar proxies applied to it. So now any pods that are deployed in this namespace will automatically get that Sidecar proxy, and Istio will be able to manage them. kubectl describe namespace default, and we see we've already got that label. Istio injection enabled is true. Okay, so now we can deploy a sample application. Linkerd had a sample application as well, but we focused on the install experience instead. Here's this sample application, this book info project. Now, the book info project has this really elegant mechanism. We have an ingress, we have a product page. The product page will reach out to one of these three review services. And in production, we would probably only run one version, but for the sake of this demo, we'll run all three simultaneously, and we'll get to experience an upgrade path through these. These review services, 2 and 3, will reach out to the rating service to know how many stars they should show. And the product page will also reach out to the details page. Now, each of these gray bars is a Sidecar proxy. And so the services will communicate through their Sidecar proxies, and that will allow us to route to the various details that we need to. So here's that bookstore page. And right now it's set in equal modes so that we can see sometimes the stars are in red color, sometimes the stars are in black color, and sometimes we have no stars at all. Version 1 has no stars. Version 2 has stars in black color, and version 3 has stars in red color. Right now we're set equally so that we'll see all three, but let's take a look at the virtual service that allows us to do this. Here's the virtual service, and it says I should route 33% of the traffic to V1, 33% to V2, and 33, well, in this case, 34 to V3. Let's instead route all of our traffic to V1. So let's do this. Let's do a kubectl apply -f. Oh, we're in the wrong folder. What folder are we in? Copy path. There we go. That's in the correct folder. Okay, so let's flip to the version 1 service. kubectl apply -f, flip to version 1. Now, with version 1 enabled, we will not see any stars at all. Now, let's assume that we got a new requirement. We've got the requirement to show some stars, and we create this version 2 service. Now, we've deployed the version 2, the pods is running, the pods are running, the deployment is set in place, but we're not quite sure how the traffic will be able to handle this load. So let's switch to this mechanism where 80% of our traffic goes to V1 and 20% of our traffic goes to V2. So let's go grab this one, and we will kubectl apply -f there. Now, because both of the pods were already up, we can see that 4 times out of 5, roughly, we'll be able to see no stars. And 1 time out of 5, we'll be able to see the stars in black color. Okay, so looks like that went well. Our service is doing okay. Let's flip all of the rest of the traffic to V2. Now, we could definitely do that slowly, but in the case of this demo, let's just go for it. Rename, copy that content, and let's say kubectl apply, and let's go to version 2. And now all of our traffic is on version 2, and we only see stars in black color. Okay, we got a new requirement. Now we need to show stars in red color. So let's spin up version 3. We've got our deployment in place, our pods are running, everything's ready to go. And so, well, now let's test it out on some beta users. Let's create a canary release or a beta channel. So for the user Jason, I'm going to hand them version 3. And for the rest of the users, I'm going to hand them version 2. Now we could choose to authenticate them based on a session cookie or based on the presence of a header or other details that we might grab from a previous service that we choose to embed in this request. But in this case, we're going to go based on that authentication details. Okay, so kubectl apply -f. Let's flip over here. And now we're in that spot where version 2 is the default. We are unauthenticated. We're still getting version 2. Everything is great. Let's log in. I'm going to log in as Jason, and I'll put in their password. And now Jason is logged in. And now we see all the stars are in red color. If I continue refreshing, I will continue seeing version 3. Great. Okay, it looks like version 3 is working. Our users have signed off on it. Let me sign out. And now when I'm not authenticated, now I will continue seeing version 2. Let's flip over completely to version 3. So here's version 3. And I will grab this and kubectl apply. And now here we're on version 3, and we can only see the stars in red color. Now that we've moved over to version 3, we can slowly drain version 2 and eventually kill off the pods and the deployment associated with version 2. Now, what's really elegant here is that we had no downtime, no dropped requests, no outage as we flipped the switch. We just slowly transitioned the traffic from version 1 to 2, from 2 to 3. We could create this beta channel if we needed to, and that was perfect. Now I'm going to flip back to the one that goes equally between the 3, because that'll be helpful for a future demo. Let's flip to the 33, 33, 33. And similarly, no downtime. I'm now back to the spot where I've got all three. Now I probably want to do sticky sessions. In this case, sticky sessions are disabled so that you can see all three. But handing our users version 1 and version 2 simultaneously might be a little weird. We got to see a really elegant mechanism of being able to create this virtual service that routed our traffic through various versions of our product. Let's now take a look at the dashboards that are involved inside of Istio. So the cool part is Istio focuses on combining the best of open source. Istio CTL, dashboard, Prometheus. Yeah, the hardest part is spelling Prometheus. So now that I'm here in Prometheus, let me take a look at Istio request total. That's not going to work. Istio. There we go. We can see a bunch of content here in Prometheus where we can kind of grab all of the metrics associated with these services. Now that's interesting, but parsing it in this way is a little bit intense. So instead of looking at the Prometheus dashboard, let's instead look at the Grafana dashboard. So let's flip over from Prometheus to Grafana. I can't spell Grafana either. I before E, except for if it's spelled with Grafana and then it's not a PH. Okay, so we've got some Grafana dashboards, and this control plane hasn't been up that long either, but we can already see some really interesting metrics as our dashboard is able to capture the contents of our control plane. Now, because these metrics are flowing through Prometheus, we can definitely combine this with our applications metrics as well to create really rich dashboards of the content within our cluster. So we've got Grafana. That was really fun. Let's next look at Jaeger. Istio CTL dashboard Jaeger. Learning to pronounce Jaeger was also quite an adventure. So let's take a look at Jaeger. Find traces. Let's take a look at this one. Now, the cool part is we can see how the traffic flowed into our system. We can see the various services that it flowed through. We can see how services called each other. It came back to this service, it called this service. If I'm here looking at this network traffic and I'm looking for, well, what's the thing slowing things down? Well, it definitely isn't this service here. The details service is replying really quickly. The reviews service isn't super speedy, but it's not really bad. It looks like this is the product page is the one that I really need to optimize. That one is the one spending the majority of the time through my system. So being able to look at these distributed traces is really elegant to be able to track down the problem. Yeah, I'm getting a slow query in my database, but is that a database concern or what microservices led up to that? Let me follow the user's journey. Did they end up with a really odd configuration in their shopping cart that led them into this page? I can start to wander through that with these distributed traces. Jaeger is really fun. And next, let's take a look at Cyral. Now, what I like about Cyral is that Cyral will graph our traffic through our system. Now, it is looking at live traffic, so let's refresh our product page a bunch of times and get some traffic here in place and come back to the Cyral dashboard. And now we can see, oh, it hasn't found the, or I'm not scrolling down enough. Nope. Let's refresh it one more time. There we go. Remember that original diagram that we saw at the beginning that showed how the main page hit the product page and the product page hit the details page and the product page also hit the reviews page, and it was looking at one of those three services, and version 2 and version 3 reached out to the rating service. This is a network map of the actual traffic through our cluster. This isn't what the developer thought was going to happen. This isn't what the architect wanted to happen. This is what is actually happening in the cluster right now. Now, the beautiful thing here is we can take a look at this and we can say, oh, hey, the product page is never calling the reviews service. Yeah, I remember stubbing out that thing so I could do that one test. And yeah, sorry, I left the debug code in. This is what is actually happening in the cluster, which is why when I first loaded it up and I hadn't used the cluster in a little bit, the diagram was empty because, well, there was no traffic flowing through the cluster. There we go. So Kiali is really good at getting that network topology diagram. Now we got to see kind of the methodologies and the thinking behind both Linkerd and Istio. And we can use these as kind of a good default to be able to then evaluate other service mesh options. Linkerd focused on a really elegant install experience to get the basics in place right away. Istio focused on having a plethora of features that we could turn on and off, including the best of open source. From there, you can take a look at Open Service Mesh, you can take a look at Console, you can take a look at others and kind of put them in context. Which one best matches the methodology of your organization? Which one feels right to you? You could probably take an hour a day, spin up a cluster, not that unlike what I did here, and start to play with each one and get a feel for how that cluster is working. At the point where you've decided on one, perhaps put it in a dev test cluster or a specific cluster for a project that might have less impact. Moving between service meshes is a little bit more difficult, but trying it out is really not painful at all. What we saw as we explored service mesh was this great crawl, walk, run experience. At the crawl stage, we got monitoring, logging, and service health. Because we're proxying all of the traffic through our cluster, we're able to watch all the traffic. We're able to understand when services are misbehaving, when they're unhealthy, maybe when they need to get restarted, maybe when we need to trip a circuit breaker so that we aren't sending traffic there unexpectedly. So from crawl to walk, now we get intelligent routing. We can start to do that circuit breaker. We can start to do A/B testing. We saw how we could do a canary channel as Jason was able to get to version 3 and the rest of the users got to version 2. This type of intelligent routing is possible because all of the traffic flowing through our cluster is flowing through these sidecar proxies where we can make intelligent choices. From crawl to walk to run, here with run, we get our network topology diagram. And this is amazing. This is our services explaining to us how our cluster is working. This isn't what the developer or the designer or the architect wanted to happen. This is what is actually happening. So maybe let's compare those two diagrams. Let's compare the diagram of what's actually happening in our cluster with the architect's vision of what they thought would happen in the cluster. And we can find places where maybe it wasn't implemented correctly, or maybe we've evolved since and we need to update our documentation. As we work through crawl, walk, and run, our service mesh is not just a proxy, but it allows us to do things like observe, control, and secure the traffic in our cluster. So we've talked about a lot of upsides within a service mesh. Let's talk about some of the costs of a service mesh. On the left, we have a diagram that is the traditional diagram as we pull up a Kubernetes cluster. We have our control plane, we have our worker nodes, we have a kubelet and an etcd, and finally, we have our worker nodes here inside the pods. On the right, we have our service mesh. And so we have the sidecar proxies, we have the control plane associated with our service mesh. In effect, we're about to run twice the number of containers in our cluster. Now that is a non-trivial amount of compute. If you install a service mesh, you will pay more for your compute costs. Now, granted, your Tomcat container that takes up this much RAM is going to use more resources than the sidecar proxy that just needs to compute TLS computations. So maybe you might get 1.6 times the compute in your cluster. But that is going to be a non-trivial additional cost that you're going to get by adding a service mesh. As you're looking down the checklist, it said install Kubernetes, containerize your application, install a service mesh. Do you need a service mesh? Can you justify the cost? Do you really need to observe, control, and secure the traffic in your cluster? Let's take a look at some of the content. When we observe, control, and secure, we have great visibility into all of the things happening in our cluster. We get visibility into the microservices calling each other, Unlike an API gateway that only can be that traffic cop, that bridge, that fence around our cluster, a service mesh allows us to see into both north, south, and east-west traffic. We can observe that traffic. Over time, when we learn what normal is, what good looks like, we can start to create policies that will control that traffic. Let's not call the services that don't need it. Let's not accept traffic into internal services that shouldn't accept it. Our internal function calls now have IP addresses, and we need to be able to secure traffic going into those internal methods. And finally, we can add mutual TLS to these services without having to implement it in each microservice, together with trying to get the trust chain into each microservice, rotating certificates as we need to. All of that can be offloaded to the service mesh, and we can have that ability universally applied to all pods inside of our cluster. Set that one attribute on the namespace, and now all of the pods will be able to do that. So when should I use a service mesh? Well, if you need to observe, control, and secure the traffic, a service mesh can be perfect. If you don't, maybe not. If you're running a highly sensitive workload like PKI infrastructure or PCI infrastructure, then a service mesh can be a great way to segregate that really, really secure traffic from kind of the normal traffic that may not need that level of security. Perhaps you're running untrusted workloads, and you need to be able to segregate the untrusted workloads away from your normal workloads to ensure that they don't reach into your network and observe that traffic. A service mesh can be great for being able to segregate that traffic. Or maybe you're running a multi-tenant workload. Now, Kubernetes definitely has namespaces, and you can create roles specific to a namespace, but that's specific to launching content within that namespace. Once your container is running, it can reach out into every other container throughout the cluster. That is enabled by default. If you need to be able to segment your traffic in a multi-tenant-like environment, then you can use a control plane to be able to create those namespace boundaries. Maybe you give each tenant their own namespace or a couple of namespaces, and their content can only stay within that namespace. Service meshes definitely give you that opportunity. If you need security in depth, if you really need to be able to secure all the traffic, not only from the outside coming to the edge of your cluster, but also between all of the microservices within your cluster, then a service mesh can be a really good choice. Or if you need some of that advanced routing, like beta channels, canary releases, in our case, we got to see that as we look through Istio, then a control plane can be a really good choice. But if you don't have these needs, understand that that additional compute cost may make it unnecessary to have a service mesh. If you're just starting out and you have a half a dozen microservices and they're all part of your internal product, a service mesh is probably overkill, and you can better use those resources not in just compute costs, but in maybe accelerating development features. A service mesh is a great choice to observe, control, and secure not only the traffic flowing into and out of your cluster, but also across your cluster. If you're watching this later, you can hit me up on Twitter at Rob_Rich, and you can grab these slides right now online at robrich.org. For those of you here live in the event, either virtually or here in person, what are your thoughts? What are your questions? You can post your questions here in Zoom chat, or for those of you who don't have Zoom or in the room, what are your thoughts? Good question. What is the performance hit when using a sidecar proxy? I can't say it's zero, but I can say it's minimal. The only additional cost involved in this is the latency in computing those TLS connections. If you choose to disable TLS, then it will be even more minimal than that. You might also use a sidecar to add additional authentication details. And so if you're using a sidecar for that purpose, then you've already hit the additional latency details here. In general, I haven't noticed a performance difference. Great question. Good question. If we're focusing on zero trust, isn't this kind of a requirement to have security in depth, to have a service mesh? Perhaps. And if you have a workload that needs to function in that environment where you need security in depth, you need to be able to document that not only are you doing secure connections right up to the edge of your cluster, but you're also doing secure connections within your cluster, then most definitely. Zero trust typically means less about connections between microservices within the cluster. And zero trust is usually about how did they get to the edge of the cluster? Did they go through a VPN first and the VPN authenticated them? Or did they authenticate at the ingress of the Kubernetes cluster? Either way, though, if you need security in depth, then a service mesh can be a great solution for that. Yes, good call. So how do I get this in place if my cluster is already running? I took your advice. I didn't invest in this early on. I'm now to that point where it makes sense. How do I get this started? The cool part is as you install Istio or another service mesh, it starts out by installing all the control plane. So, ramp up your nodes to be able to get that additional traffic. And then I annotate the namespace or namespaces that I want to automatically get injected. All of that doesn't impact my services at all. Now I start killing off pods and restarting them. Let me start on the inside and work my way out, or maybe I have a maintenance window that just lets me crash them all and restart them, or maybe I just kind of let them organically do that. As they start back up, the namespace now has the annotation, the control plane will inject the Sidecar proxy, and I'm ready to go. Now, the interesting thing is I haven't created policies yet. So perhaps it's connecting with the other services Sidecar proxy, or perhaps that Sidecar proxy doesn't exist yet. So I'm still okay. If I'm traveling from the outside in, then the traffic is still routing to the applicable service. It just doesn't have all those Sidecar proxies yet. Okay, it's D-Day, it's time to do it. So let me go evict that last pod that was really specific about wanting to keep its cache and live forever, thanks to the developer who made that possible. And now I've got all of my pods. They all have Sidecar proxies. Let's start applying the policies. Now, only the traffic that I want flows in the places that I want. I was able to gently ease this service mesh into place, whether using Istio or another thing, just because I'm able to put those pieces in place and only get them to take effect when I'm ready. Definitely do this in dev and test first. And then once you're comfortable with that process, then do it in production. But it's really not traumatic to move it into place. You don't need a multi-hour maintenance window. Or perhaps I'm wrong and you do. Did you have a question? Sorry about that. Go ahead. Good question. So part of the benefit of a service mesh is I can now apply it across cluster to get service discovery, service health details, to be able to grab those across clusters in a really elegant way. Which service meshes have those features? Is that your question? Good question. So how do these features compare in a multi-cluster environment? The short answer is I don't know, but the medium answer is that these service meshes are working really hard to keep up with each other. And so if one doesn't have it yet, now they do. And so the cool part about that is picking a service mesh based on their feature list is probably less advantageous. If you really have a blocker and you need that feature, then maybe you need to exclude a certain service mesh that doesn't have it yet. But for the most part, wait a minute and it will have it too. I haven't really compared the cross-cluster features of a service mesh, but I know it can do exactly that. That was a great question. I've got some homework to do now. Well, this was a lot of fun. Thanks for letting me play.